Welcome to this discussion on quantum mechanics that we have been engaged in. So, we will talk about wave function as a linear superposition of basis sets. We will talk about the postulates of quantum mechanics, the properties of the wave function. We will tell you what operators are, in particular the Hermitian operators, the commutation relations, expectation values, the quantum dynamics, how the wave functions evolve with time and the operators evolve with time. And finally, we will talk about different representations which are known as the Schrodinger representation, Heisenberg representation and interaction representation. Okay. To start with, we once again remind you of the probabilistic interpretation. The first picture on the left has been shown to you. It is a interference pattern of two slits. This is called as a Young's double slit experiment, and what you see on the right is the interference pattern on a screen which comprises of alternate dark and bright bands, and these two slits they are taken as coherent sources, or they are considered as coherent sources, and that is what creates the interference pattern on the screen, because of the path difference that the light has to travel from the slits to the screen, and this path difference will give rise to phase difference, and this phase difference being sort of even integer times lambda or odd integer times lambda, that will decide whether you have the bright fringe or the dark fringe and so on. That is the classical explanation coming from optics. What we have used it is to make sure that the photons are allowed to go through both the slits with certain probability, with in fact half probability, such that they can interfere on the screen. And if you block one screen, which means that you are trying to make sure that the photons have gone through only one slit, and that would not give rise to an interference pattern, which is what we have discussed earlier. Okay. The right picture is about a cat, okay, and it is called as a famous Schrodinger's cat experiment. The cat is kept in a room, and there is this green colored apparatus that you are seeing, or that is a container. That container contains poisonous gas or a poisonous liquid, and there is a hammer kept in the vicinity of that. So, if this cat goes and breaks the container, the poisonous liquid will spill out, and that will cause the cat to die. And if the cat is itself, it desists from doing such a mischief, then the cat will be alive, and you lock the room, and then you come back after some time to find, let us say, the cat is alive, which means that he has not done anything, any mischief, or it has not broken the poison vial. Now, that tells us that before you have made this measurement, that is, you have gone and opened the room, in your mind it's the state of the cat is in a superposition of dead and alive states, just like the two slits that we see here. It is dead and alive. These are the two states of the cat, and once you make a measurement, the measurement will force the system to assume one of the eigenstates of the system, that is, suppose it is alive. Okay. And so, we are talking about probabilities. So, the probabilities would exist as long as the measurement is made, or before the measurement is made. So, as long as the measurement is not made, it is in a probabilistic state. For example, you see that a coin being tossed, and the coin goes up in the air, and till it comes down and falls on the hand or on the ground, one does not know that whether it is going to be a head or a tail. And it is important that we keep it that way in order to have the probability interpretation persisting. But it is also important that once when the measurement is made, that is, the coin lands either on the palm or on the ground, you are sure that either its head or its tail. Okay. So, there is an observer which is making this measurement to collapse of to one of the states of the system, and these states are called as the eigenstates. Let us talk about that in more details. So, the outcome of this measurement will make the system collapse onto one of the possible outcomes. For example, the cat being alive, for example, the result of the coin toss gives you head, and so on. So, the observer really plays an important role in this whole thing. So, these possible outcomes have a technical name, and they are called as the eigenstates of the system, or the states of the system that I said. State means the state of being dead or the state of being alive is the state for the cat, and for a given quantum system, this states will be called as the eigenstates. And here in all these examples that we have given, there are only two possible eigenstates, namely the dead and alive, namely the the head or tail and so on. But in general, in a quantum system, there could be many eigenstates that are possible. Okay. So, as you make a measurement, the system collapses onto one of its available eigenstates or possible eigenstates. In this connection, we will extensively use a notation that I simply introduce here. It is called as a Dirac's bracket notation. The word bra and ket, they are used by Dirac just to have a split of the word bracket. That word C is not there, the letter C is not there. So, you have a bracket and you just remove this, and this is how he represented these two states of the system, and these are the eigenstates of the system. So, the notation used by Paul Dirac in quantum mechanics as a way to make linear algebra operations more appealing and simpler too, and it consists of rewriting the usual inner product in a style that gives out more information. And what is an inner product? The inner product, if you look at the picture that is given, say psi is a vector which is pointing in the direction that is shown by this yellow line, and phi is also a vector which is shown here in green color, and an inner product, that is phi psi, is simply the projection of psi on this phi, and it is given by this this line that you see here. And so, that is the projection, or that is the inner product of two vectors, and the inner product of two vectors is written technically as an integral from minus infinity to plus infinity, and a phi star psi and integration over all the coordinate variables. And we are writing it x here, but it could be r, a 3-dimensional integral, but here just we are talking about just 1-dimensional vectors, that is say psi and phi both depend on only on x. So, how are these postulates of quantum mechanics that are proposed, how are they helpful, what do they convey? Let us see this. There are many postulates, some of them may be very trivial for you, but they were postulated at a time when quantum mechanics was just developing, it is being developed, and in those days these postulates were very helpful, and they lay down the guiding principles of the development of quantum mechanics. The wave function psi is a solution of the Schrodinger equation. So, this is a wave function is what we are talking about, and it is in general a function of r and t, and then we will see that it is not only a function of r and t, we can go to another space in which it is a function of momentum and energy, or k and omega or p and omega, and so on and so forth. So, is the solution of this Schrodinger equation, which is nothing but h psi equal to I h cross del psi del t. From some plausibility arguments, these have been derived. In fact, they are just consistent with the energy quantization and the de Broglie relation. So, de Broglie relation is P equal to h over lambda, and E equal to h nu is the energy quantization that has been used by Planck, and later on employed in the study of photoelectric effect by Einstein. Okay. So, psi is a function of space and time, as I told, and it obeys the psi mod square integrated over all space. Now, we have shown it in a 3-dimensional space. If you want, you can write in 1 dimension as dx. So, this dx and cube r, they mean the same thing, and this is for all t. Okay. So, at each t or at all time, this normalization condition will be satisfied. Okay. The second postulate says that to every observable there exists a linear Hermitian operator. Okay. And these are very important things. One is that it's a linear operator and it's a Hermitian operator, and what we mean by Hermitian operator, we'll see that. But what it really means at this level is that the Hermitian operators are associated with the observables, and which should yield real eigenvalues. So, these Hermitian operators have real eigenvalues. We haven't defined this eigenvalue or an eigenequation, which we'll shortly do it. Before that, I thought it's more useful and relevant to put down the postulates. In the measurement of an observable, the corresponding operator will yield only the eigenvalue, and this is just to bring context from the discussion that we had earlier, that the measurement is to see whether the cat is dead or alive. Okay. And psi has two states, or rather psi comprises of two possibilities. One is that it's dead or it's alive, and A is this measurement of observing it. So, that's the operator that observes that what's the status of the cat if you have left it, say, for some time, and this is the eigenvalue. Okay. So, the eigenvalue corresponds to whether the cat is dead or it is alive. Suppose if it is dead, then let's call it as that as 0, and if it's alive, let's call it as 1, or if it's head, let's call it as 1, and if it's tail, let's call it as 0, and so on and so forth. Okay. So, where psi is called as the eigenfunction and A is known as the eigenvalue, and this one is called as the eigenvalue equation, and it can also be written in terms of this Bra and Ket notations as A psi. Okay. And so, there is another postulate that comes over here, that is the expectation value of an operator, and this expectation is expressed as inside this angular brackets, right and the left angular bracket, or left and right angular brackets. So, it's like this. Okay. So, any operator O, here we have written A, is really the integration of this coordinate variables from minus infinity to plus infinity, and they are squeezed between the wave function or the eigenstates of the particle. Okay. So, so these are the states, psi's are the states of the wave function, and A is taken between the two, or squeezed between the two, that is between the left eigenvector and the right eigenvector, and so this is the definition of the expectation value. The wave function is symmetric under the exchange of particles for if the particles are bosons. Remember that we are talking about indistinguishable particles. They are identical and indistinguishable, but while they are identical and indistinguishable, they have two possibilities. One is that they can be either bosons or fermions, and bosons are characterized by even wave function. Even means that if you have psi of x, I am just ignoring the t for the moment, if you change this x to minus x, that is called as the even function, and if this thing changes from it, if you change this, it is called as an odd function. That is not exactly what we mean as symmetric. So, this is called as the symmetric and this is called as the antisymmetric. We just gave you an example, but what we mean to say is that we have two particles, say for example x1 and x2, and you change that to you swap the two particles or interchange the position of the two particles, and whether you get a plus sign or a minus sign will decide that whether they are bosons or fermions, and the plus sign is reserved for bosons and the negative sign is reserved for fermions. And in fact, you might have heard of the Pauli's exclusion principle, which the electrons have they are bound to obey that, and in that it says that the no two particles can actually be in the same state. Okay. And this can be understood if you write down say for 3 particles, if you write it down in terms of a Slater determinant, and the Slater determinant would say that if you write any determinant and make either 2 rows or 2 columns to be identical, the same, then the determinant is equal to 0, which means that if the positions of the 2 particles are same, we are not talking about spin here. If you allow for spin, then of course a spin up and spin down can still occupy the same position, and in that case the wave function will be equal to 0, which means that this is strictly prohibited for the electrons for 2 of them to occupy the same quantum state with all their quantum numbers to be identical. This is just a table of certain observables and their corresponding operators, and this what kind of operation should you do is stated here. So, if you are talking about a position variable, we denote it by r or by x, and the operators are written with a hat usually, but in most of these cases when we write the operators, we will neglect that hat. But if you want to be very sort of strictly correct in these notations, then you should write it with a slight hat that you see here, and that is the hat that we are talking about. So, position variable is the symbol is r, and then the operator will come with a r cap, momentum is p cap, kinetic energy is set t, it is t cap, and it is important to see that the momentum has is of course a vector operator which has a form in the coordinate space equal to minus IH cross del x in the x direction, del y in the y direction, and del z in the z direction. The kinetic energy has a form minus h cross square over 2m del square by del x square plus del square by del y square plus del square by del z square. The potential energy is V of r. It has no form. I mean, if it is say for a particular problem, say for example the linear harmonic oscillator, this has a form half m omega square r square. It just simply multiplies this half m omega square r square by the I mean that's multiplied with the wave function and so on. The total energy in the time independent case is given by so the symbol is H, which is the Hamiltonian, which is what we will see very extensively, and the eigenvalue of that is called as the energy or the total energy, and in the time independent form it is written as minus h cross square over 2m del square del x square plus del square del y square plus del square del z square plus V of r. Then there are angular momentums, they are often written with capital Lx, Ly, Lz, and they have these form that are said there, I mean that are written here. So, it is basically you can get it as r cross p, and the x component of r cross p, where r is given by so this is x I cap plus y j cap plus z k cap, and so if you write that r here and p as these ones that are said here in this particular line, then you would get this x component of the angular momentum to be like this, y component to be like this, and z component to be like this. Okay. All right. So, let us do some preliminary linear algebra in order to sort of note down the properties of this wave function and what kind of information do they give and what are their derivatives. Derivatives means what else can we infer from them. So, we have this psi RT, or you can call it in one dimension we can call it x of x and t, or in another space we can call it as k and omega. Okay. And k, if you are talking about a 3-dimensional vector, k has to be written as a vector, but you can if it is you are dealing with one dimension, then that is a scalar. So, what is k? K is nothing but p is equal to h cross k, and p of course is the momentum of the particle which has relationship with the wavelength, that is p equal to h by lambda, and all these are embedded into the Schrodinger equation that we have talked about, whose solutions are all these psi's and so on. Okay, so, what is the eigenvalue equation? And the eigenvalue equation is an equation like this, that the Hamiltonian, it was written with a curly h. If you look at this earlier figure, it is curly h, but we will write it with a straight h. So, h of psi, that is a ket psi, this is equal to E of psi, and this psi is a wave function, and this wave function can be expanded in terms of the basis sets. Okay. So, wave function and what I mean by that, there is an important statement, and these basis sets are all these different states, possible states of the particle which are which were there, like for example, the dead or alive, or the head or tail, or the top slit and the bottom slit and so on. So, that is written as, so the wave function is really written as some C n phi n, where C n's are the coefficients of this expansion and in general complex. So, the C n's are in general complex, and phi n's are the basis sets. So, as soon as you make a measurement and you find the cat to be alive, the C n corresponding to it being alive, that will become equal to 1, and the C n corresponding to, or the coefficient corresponding to that it being dead, goes to 0. Okay. So, this is now this psi is normalized. This is what the normalization means, and if you write it in terms of the integrals, it means that it is just the inner product that we have said. So, the inner product of any vector with itself has to be equal to 1, right. So, this is, I am writing it in one dimension, this is equal to 1, and this is what it should be, because this is also the probability, because psi star psi is the probability density, this is called as a probability density, and this probability density integrated over all space, that should give us 1 for all time. Okay. So, psi is a function of, in general, a function of x and t. So, this is true for all time. So, we are not writing time here explicitly, but in terms of the linear vector space, or in terms of this vector algebra, the inner product of one vector with its own self is equal to 1, and that would be giving us this relation, that is inner product of psi with itself, that is bra psi and a ket psi, that is equal to 1. So, if you put that here, you have a psi and a psi, that let us call it as equation 1, this is equation 2, and this is equal to n, and then we have these C n square, and we have a phi n. Okay, let me write it a little more sort of explicitly. So, when I take the inner product of two vectors, and each of the vector is actually can be decomposed as this C n phi n, I should write it with two indices, with the C m star C n and a phi m star, a phi m bra and a phi n. And now this for these each of these vectors are orthogonal to each other, and they form a complete set. And if it is an infinite dimensional space, that is each of these phi n and phi m the labels corresponding to them, I mean they sort of represent infinite number of such states. We just talked about two of them, like being alive and being dead, but suppose we are talking about another system, there are very large number of possibilities that the system can actually go to, in principle infinite of them. Then these phi n and phi m, they belong to a linear vector space with a special name. The special name is called as a Hilbert space. Okay. Okay. And because I said that they are orthogonal, so this has to be equal to 0 if m is not equal to m is not equal to n. So, this is written as a Kronecker delta, which is delta mn. So, delta mn is equal to 1 for m equal to n, and it's equal to 0 for m not equal to n. Okay. And this is exactly what we said about these orthogonal, their orthogonality. So, which means that if you think in terms of vectors, these basis sets are also vectors as well. That is what it gives. I mean these the vector property of this psi is given by this vector form of the phi's. Okay. And so, this is they are orthogonal and also normalized. So, that is why they are called as, this psi is called as an orthonormal function, and this if m is equal to n, then only it survives, then this becomes equal to n and C n mod square, because m and n are same. Otherwise, it is of course equal to 0, then it does not make sense to write this. And so, this is equal to 1, because that is what is obtained from 2. So, equation 3 says that sum over n C n square is equal to 1. So, if you apply that to the coin tossing problem, say for example, and in that case you have the half probability to be equal to find it in the head state, and another half probability that you would find it in the tail state. I am saying state because these are really the states of the system, and so they would add up to equal to 1, and that is why 1 by root 2 is equal to C n. So, the probability is C n mod square, which is half. So, the coefficient, when if you want to write it for this head and tail, so the wave function or for this coin will be in this 1 by root 2, and it will be in the head state plus, so I am writing a head with a h, and 1 by root 2 in the tail state. And when you make a measurement, one of them will, one of the possible outcomes you will get, and when you get a possible outcome, then of course one of the C n's go to 0, and the other C n, that is this coefficient, becomes equal to 1. Okay. All right. So, we have said about this some basic preliminary properties of these basis sets, and these phi n's are also linearly independent, or even these phi n's are linearly independent. Okay. And that is why if you have a psi say prime, okay, we can write it inside, psi prime is equal to some constant into psi. So, in that case psi prime and psi are linearly dependent. Okay. So, in that case they are not independent. So, what we mean by independent is that suppose there are three, we are just talking about a three-dimensional space. So, there are C1, C2 and C3. So, there is this C1 phi 1 plus a C2 phi 2 plus a C3 phi 3 is equal to 0. Okay. So, then if this is true, then C1 equal to C2 equal to C3 equal to 0. So, that tells you that the vectors are, or these basis sets are linearly independent. Okay. So, let us try to understand more about these basis sets, because this will give you a more in depth understanding of what we are trying to sort of relate to, and what do they mean. So, let us talk about an outer product of this, and this outer product, unlike the inner product is a scalar, the outer product would be still a vector. So, outer product and what we called as a change in basis. Okay. And we want to a priori talk about a property, that is stress of an operator, or the expectation value of an operator is independent of the basis. So, this expectation value we have talked about already, they mean that this A is equal to psi A psi. So, which means that they are taken between the two psis, and you are talking about these as they are the matrix elements, and these matrix elements, and we are really talking about the diagonal matrix elements, because these two psis are same, and so this is actually called as a trace. Okay. So, trace of A, and this trace is the sum of the diagonal elements. Okay. And this trace is independent of the basis chosen, because trace of a variable, or rather of an operator, should be independent of which basis you write, because that corresponds to a sort of physically observable quantity. Okay. So, we can write this down as the outer product as there is a C n and a phi n, which is what we have written, and we introduce now a different basis, which is n. So, that is like a C n and a chi m, a different basis, and we have to use a chi m and then a phi n. Okay. So, this we could introduce because the outer product of this two vector is equal to 1. So, we have not done anything, but we have just introduced a 1 inside. But in that case, what we have done is that we have gone from an old basis phi n to a new basis, and what we can write down is that so this C, this can be like m and C m prime and chi m, where this C n and chi m and phi n, all these are scalar quantities. In general, complex quantities is written as C m prime, C prime m. it is not, the prime is not with m, but the prime is with C, which is a new coefficient that depends on the new basis. So, we have gone from a basis of phi of n to a basis which is chi of m. Okay. And now, we will show that the trace is invariant of the basis that is chosen. So, its trace is invariant of the basis, and let me show that. And why it is so? Physically, trace actually means that this is sum of the diagonal elements, or it is basically the matrix elements of the operator between the like states. That is, when you have same states, it's been same states are used here. So, this is the definition of the expectation value in terms of the trace. So, phi n's are some basis that we are using. Now, we will show that we are going from a basis which is phi n to something else, and we will see that that this expectation value does not change. So, what we do is that we use this n and let us use n, m and p, and let us introduce these phi n, say for example chi m and chi m here, and then you have a, and then let us use another basis, let us call it as a gamma p, and then use this gamma p and then phi n. So, what I have done is that there was a sum over n in the initial expression, and then I have introduced two dummy sums which are m and p, and use this chi m, the outer product of which is equal to 1, and the outer product of gamma p is again equal to 1 sum over p. So, I have just introduced two ones there. Ones means these identity matrices, and then what we do is that we can write this down as n, m and p, and bring this at the front. So, we have these, because all these are inner products, which means that they basically talk about the length of the vector. So, that is a scalar quantity. So, we can swap its position. So, this is bringing it to the front here, will tell you that this becomes equal to phi n. Then we have a gamma m and a gamma m a, and so this chi m, and then there is a gamma p. Okay. So, this gamma p phi n chi m a gamma p, where all these phi n is a basis, chi m is another basis, and gamma p is another basis, and they all come with different indices, which has been shown here. Now, you see that we can use this sum over n and these outer product of the phi n, the original basis that we have written, we can make that equal to 1, and this will go away, and then we have m and a p, because we have taken these n into account, and then we have a gamma p, and we have a chi m, and then we have a chi m, and then a, and then gamma p. And now what we can do is that, again, this is an expectation value that can be brought here. So, this can be written as m and p. We have this chi m a gamma p, and then we have a gamma p chi m. Once again, I can use this outer product to be equal to 1, that along with this summation over p. So, that leaves me with a m and a gamma m a gamma m. So, we have indeed gone from a basis which is phi n to a basis which is gamma m, and we are still writing the expectation value in terms of sum over n, and these a, the operator a is taken between these chi m's, and that is what is going to be important for us. So, that tells you that trace is invariant, and it does not depend upon the basis that we choose to express. So, trace is as you know, that is a sum of the diagonal elements. And so, okay, let us look at this, say for example, the Hamiltonian operator and how it looks like and so on. And I will give you a simple example to construct this Hamiltonian operator. And remember that each of these operators are nothing but matrices. And when you talk about a matrix, you need to talk about a basis. Like if I give you a for example, some data here in the x and y axis, some data are written there, say A, B, C, E, F, G, H, I, J, K, L, M. Okay, so, it is a 3 by 3, and we have written down some numbers, or these just some some letters have been written down, and these letters do not mean anything to you if we do not say that what is recorded in the x axis and what is recorded in the y axis. In the x axis, we can record the marks of various students, and in the y axis we can note down their roll number, and then that will make sense that a particular student with a given roll number has gotten so much in some subject and has got some other number in some other subject. So, this is called as a basis. Basis is the representation, or this makes this description of an operator complete, and we need such a description for all the operators. And in particular, let us talk about the Hamiltonian operator, which forms one of the major sort of discussion point of discussion for us in the study of quantum mechanics, because the eigenvalue of the Hamiltonian operator gives you the energy, and this energy is an important quantity, because the energy will tell you that whether the system is in the bound state or it's in the excited state, and what are the different energy levels. Those different energy levels will decide whether whether there'll be transitions possible from one state to another, and if it does, then what kind of energy is required, or there is a particle which falls from one energy state to a lower energy state, say for example, and then a photon is, or a gamma is emitted, what's the frequency of the photon, and so on. So, we need to know the total energy of the system, and as I said, very importantly, if the total energy is negative, it corresponds to a bound state. Okay, like for example, we'll see that hydrogen atom is in the bound state. So, the electron is bound to the atom, and the electron cannot escape unless you give it a sufficient amount of energy. All right. So, let us talk about say force, either you can say sites, and these 4 sites are written as they are numbered as 1, 2, 3 and 4, and now I am going to write the Hamiltonian operator in terms of this. So, we can have terms connecting 1 to 1 itself, 2 to 2, 3 to 3 and 4 to 4. There could be on-site terms which can get into the energies, say for example, the chemical potential, or for example, some other kind of on-site energy. Usually these on-site energies are called as a chemical potential, and there could be cross terms which are like 1 to 2, 1 to 3, 1 to 4 and so on. So, one can have terms where I is equal to j in the Hamiltonian matrix, and one can also have terms which are I not equal to j. Okay. And it is very easy to see that I can write this down as 1, 2, 3, 4. So, this will form my basis, which are nothing but the positions in the real space in this particular case, say for example. Okay. So, we have these 1, 1. So, there is 1 H1 where Hamiltonian is written by H, as I said earlier, and then this would be like 1 H2, and well, I mean you can write it 1 H2, or you can also write it, because you want to consider this as a bra. So, it is a 2 H1 and then 3 H1, and then there is a 4 H1 and so on. So, these are the matrix element of the Hamiltonian operator, depending upon what kind of rules do you set for if there is a connection between the lattice sites 1 and 2, then this term will be equal to non-zero. If there is no connection between 1 and 2, then it will be 0. Say for example, this is very easy to see that this can be 0 because it is not a nearest neighbor, it is that diagonal neighbor and so on. So, this can be written as 1 H2 and so on and so forth. Okay. 1 H2 and this is like 2 H2. Let me write down all of them, so that so this is 3 H2 and this is 4 H2, then there is 1 H3, then it is 2 H3, then it is 3 H3, that is the diagonal element for this, and then there is a 4 H3, and finally we have 1 H4, and we have 2 H4 and a 3 H4, and finally the diagonal term 4 H4. Okay. So, this is the Hamiltonian matrix written in this basis. If you know the rules of connecting one lattice site to another, then you can calculate these matrix elements and you can construct the entire Hamiltonian matrix, diagonalize it, you will get the eigenvalues or the energies of that system comprising of say these 4 particles or 4 lattice sites. Okay. All right. Let me tell you that what are these eigenvalues, because if you make a measurement of a system by an operator that corresponds to an observable, you will always get this eigenvalue as A. Say for example, if A psi, so we will call it as eigenvalue, the discussion. If you have A psi, this is equal to A psi, where A is the operator, psi is the eigenfunction, A is the eigenvalue and returning back the eigenfunction. So, an operator operates on the eigenfunction, returns the eigenvalue corresponding to this eigenfunction and returns the eigenfunction itself. So, this if I want to calculate the expectation value, then this is equal to psi A psi, and I have simply psi A psi, but this A is just a number. So, this becomes A psi psi, and because psi psi is provided it is properly normalized, this is equal to A. So, that tells you that A square is equal to A square. Okay. And if I want to calculate what is A square psi, then that means that it is equal to A psi, and then it is equal to A square psi. Okay. And if you want to calculate the eigenfunction of A square, or rather the trace of A square, or the expectation value of A square, then this is equal to A square. So, the this fluctuation in this A is now given by square root of A square average or expectation minus A average this, and both are A square. So, this is equal to 0. So, which means that there is no fluctuation in the value that is obtained by the measurement of A. Of course, we are not showing that delta A has to operate on something, but if you just write delta A acting on a state, this will give you a 0 into psi, which means that delta A has eigenvalue equal to 0. So, this means of course, two things, that psi is an eigenstate of A, and no matter how many times you make this measurement, you will still get it this fluctuation to be 0, which means that this is the only measurement, the result of the measurement that you get. Okay. So, let us check out the Hermitian properties of matrices. Of matrices means operators, and in particular we will show that the momentum operator is a Hermitian operator. And why is this question being raised? Because you have seen it earlier that P is equal to minus I h cross and d d x. Of course, you can write it del del x, and if you want, you put a cap on that, because these are operators and we are writing it only in one dimension. If you write it in 3 dimension, of course, there are del d d y d d z that will be there. And because it looks like that there is a this term which is I, and how in that case this becomes a Hermitian operator, which means that it will return real eigenvalue. If it retains, or rather returns real eigenvalue, then of course it's a Hermitian operator. So, a Hermitian operator is generally, they are recognized by this relation that your A dagger I j, this is equal to it's equal to A j I star. Okay, so that means that So, what is the meaning of taking a dagger? Dagger is that you take a complex and a transpose. Transpose is the operation by which you interchange rows and columns of a matrix. So, this is a test of hermeticity. So, let me show this for the momentum operator. So, we take this momentum operator between two eigenstates of the system, which let us say they are psi 1 and psi 2, and we write it in the good old notation introducing these integrals. So, this minus infinity to plus infinity, because there is a brass eye we will have to write it as star, and then the operator which we have decided to write it in one dimension, and such that this integral is just one dimension. There is no loss of generality, because you can trivially extend it to more than one dimension. Okay, and this is equal to minus I h cross minus infinity to plus infinity, and psi 1 star and d psi 2 dx. That is d dx acting on psi 2, whatever is there on the right of d dx will act on that, and this. So, now how do we evaluate this integral? We can do it by using the integral by parts. That gives us that minus I h cross is equal to psi 1 star and psi 2 minus infinity to plus infinity, and minus of psi 2 d psi 1 star dx dx. Okay. So, that is the result for this. So, you take psi 1 star as the first function and d psi 2 dx as the second function. So, integral of so u v dx is equal to u integral v dx minus du dx and integral v dx the whole dx. That is the form for the integration by parts, and this is equal to 0, because for the finiteness of psi, the product of these two cannot oscillate or cannot be finite at infinite at plus infinity or minus infinity. That takes away this absorbing the negative sign there. So, it is a I h cross psi 2 d psi 1 star dx and dx. So, this is nothing but psi 2 and p and psi 1 star. Okay. So, psi 1 p psi 2 is equal to psi 2 p psi 1 star. So, this tells you that you have taken transpose, because you have interchanged the row and the column, and then also have taken this star, and this is exactly what I said, that is the test for the hermeticity of an operator, and this hermeticity ensures that it will return real eigenvalues and it should correspond to an observable. Okay. So, in simple notations you can say that for any operator, if A is equal to A dagger, this is called as the Hermitian operator. Okay. There is another thing that one should be familiar with. If you take a B dagger, it is taken in from the other way. So, it is equal to B dagger A dagger. So, this because these are matrices, and you have to be careful while multiplying these matrices, because matrix multiplications usually do not commute. So, A B is not equal to B A. So, A B whole dagger, that is equal to a, first you have to take it is on the, this is called as a cyclic property of the matrices. Okay. So, let us talk about the commutation relation between operators. Okay. So, and again we show it with two specific operators. So, when these two operators for two general operators, if A and B equal to 0, it tells you that A and B have same eigenfunctions, but they of course do not mean that they have same eigenvalues. They can have different eigenvalues, but they have same eigenfunctions, or it sometimes said that they can be simultaneously diagonalized. So, they mean the same thing, and of course, the commutation of two operators play an important role in all of quantum mechanics, because if this is true, then your A B equal to B A, because this commutation means that, so commutations of two operators can be written as, it's a A B minus, written in the reverse form, it's equal to B A. If this is equal to 0, then A B equal to B A. So, you can actually interchange the order in which you write these operators, and as I said that they are matrices, and usually matrices do not commute, but these operators, if they commute with each other, then their corresponding matrices will commute as well. So, let us see that position and momentum operators, and again one will write it in the one dimension. So, position and momentum, and what kind of relationship do they have. So, let us check out this famous commutation relation x and p, and this x and p commutation is not equal to 0, which means that x and p cannot be simultaneously diagonalized, and the reason that they both are infinite dimensional matrices. So, how do we show that they, and what values do they have if they do not commute? That is an important thing. So, this is equal to x p psi minus p psi x, and this is equal to x minus I h cross d d x psi, and minus, so this is minus I h cross d d x psi x. Okay. Remember, psi is of course a function of x and t, and this is the position operator. So, in principle one should put a hat on this, as I said earlier, that neglecting all these hats, but if you feel more comfortable in denoting these operators to be, so that they become more explicit for your own understanding, please go ahead and do that. And so, this is equal to minus I h cross x d psi dx. See, minus I h cross is just a scalar quantity, and then so this is equal to a plus I h cross, and now I have two terms. I have a d psi dx and plus I h cross x d psi dx, right, because there are two functions psi and x, and I have to take a d dx of that. Both psi and x, they depend on x, of course x depends on x. So, d dx of x is equal to 1, that gives rise to this term, and the other term keeping x to be constant and taking a derivative of psi with respect to x. So, the first and the last term, they cancel, giving rise to plus I h cross, not minus, I h cross and a d dx of I mean it's I am sorry, I have written it. So, this is equal to psi, not d psi dx, because you keep the psi constant and then take a d dx of x, which is equal to 1. So, this is this simply equal to I h cross psi. So, that tells us that x and p commutation acting on psi gives I h cross psi. You can treat this as this eigenvalue equation, which tells you that x and p, this is equal to I h cross. So, that is the commutation relation between x and p, and this has been told earlier that because they are canonically conjugate variables, they do not commute. Okay. So, let us next step, let us look at how we can actually talk about the quantum dynamics, or rather how do we sort of talk about the time evolution of operators, because we have so far talked about how the psi depends, I mean its dependence only on x, and we have not talked about the time evolution. So, this is called as quantum dynamics, or we can just talk about the time evolution of psi, and this quantum dynamics can be obtained if you this psi at a later time t can be obtained by multiplying it by a unitary operator and on the wave function at time t equal to 0, okay. Or you can write it, because usually it is not only evolving it from time t equal to 0 to a time t equal to t, it could be from a time t equal to t1 to time t equal to t2. So, let us use two indices here. In this case, one of them is t, the other is 0, and this psi of 0. Okay. So, we will actually find a form for u of t 0 and we will do it in two different ways. So, one is that so a psi of t, which we have already written earlier in terms of its basis states. So, there was a C n and a phi n, we just kept it vacant for a while. Now, these phi n's are the basis states, and it is usually sort of chosen, these basis states are chosen such that they are independent of time, and the whole time dependence really goes into the these coefficients C n of t. And so, this is nothing but u t of 0, say for example, or let us just take a t 0. So, that it is not always 0. So, psi of t 0. Okay. So, you are evolving it from a time t 0 to a time t, or you can evolve it from a 0 to a time t. It does not matter, just to make it more general that we have written it that way. Okay. So, you know that at all times this psi of 0 should be equal to psi of t, and which means that the normalization would hold at all times. This is what we have said. Now, that gives you a property of these matrices, where you say that your u dagger t t 0 is equal to u t t 0, this is equal to 1. Okay. So, this is called as a unitary operator. And this tells you that the time evolution operator is a unitary operator, where you have considered that psi at a later time t can be obtained from a psi at an earlier time, either say at t equal to 0 or t equal to some t 0, by operating it by an operator u t t 0, where u t t 0 is an unitary operator which has got a form which is u dagger u equal to 1. Okay. And why did I write it as a 1 with a bold sign or with a sort of double strand? And the reason is that this is not just 1, but it is a identity matrix, or it has all the diagonal elements equal to 1 and all the diagonal elements equal to 0. And the dagger has already been told that the dagger means that you take a transpose and you take a complex conjugate of this. So, so u dagger u is equal to 1 is an important property, and there could be another important property that you can think of, is that this can be successively. So, you can do it like t2 to t0. So, it is from an initial time t0, you can go to t2 to a final time t2 in 2 steps, where you do it as t2 t1 and u t1 t0 and so on. So, you can really successively build up this time evolution from initial time t equal to t0 to then to t1 and then to t2 and to t3 and so on and so forth. Okay. So, here of course, it is understood that t2 is greater than t1 is greater than t0. Okay. So, we will have to find a form for this, and how do we find a form for this? You have to note that let us talk about an time evolution. Okay. So, it goes, so limit dt tending to 0. So, it sort of evolves from t 0 to t 0 plus dt, and if that is true, then so dt tending to 0. So, that is called as the infinitesimal time evolution, okay, or dt going to 0 means that dt is much smaller than t 0, okay, and let us see how that can be handled. So, you have psi of t 0 plus delta t, this is equal to u t 0 plus delta or dt. I am writing it as okay, you can write it as dt, they mean the same thing, it is a small thing. So, either delta or d does not matter, and t 0, this is psi acting on t 0, and so now in the limit dt going to 0, you can take that t 0 plus dt t 0, this is equal to 1. 1 means again you have to be careful that this is equal to an identity matrix, and so these requirements would be satisfied if you have this u t 0 plus dt and t 0, this is equal to 1 minus some I omega dt. We do not know what omega is, but then we can figure it out later. So, this as dt goes to 0, then we have this u t 0 t 0, which of course would be equal to 1, because you are not evolving the system at all. So, psi of t 0, and if you want it to be connected to be psi of t 0, you simply should put a 1 here, and this 1 is nothing but a u t 0 t 0. So, u t 0 t 0 equal to 1. So, you going from u t 0 plus dt to t 0 is 1 minus I omega dt, and so omega has to be is a Hermitian operator, and why omega is a Hermitian operator, because we have this u to be a unitary operator. So, that is why it has to be a Hermitian operator, because you understand again this is not really 1, but it is like a 1 identity matrix, and so this means that omega dagger is equal to omega. So, we have these u dagger t 0 plus dt t 0 and u t 0 plus dt t 0, this is equal to 1 plus I omega star dagger dt into 1 minus I omega dt. So, this is equal to 1, and if of course, we neglect terms which are of the order of dt square. So, where of course, we have used that omega equal to omega star. So, now sort of this omega can be identified. So, u t 0 dt or u t t 0 is really dimensionless, and if that is true between any two times it is dimensionless, then of course, your omega has to have the dimension of inverse of time, or it has to be sort of which is known as a frequency. Okay. So, omega has to have the dimension of frequency, and when we talk about frequency at the back of our mind, if we use this E equal to h nu, so this is like E over h, and this really in the operator notation should be equal to the Hamiltonian by h. So, that tells you that the u t t 0 has a form which is equal to 1 minus I h. Well, I mean this is t 0, this is for the infinitesimal operator. So, this is t 0 plus dt and t 0. So, this is 1 minus h by h cross dt, and if you recall that now we are talking about a small time interval. If we keep multiplying such time intervals, or rather if we add more and more time interval and go from some t 0 to some large time, we would get these kind of factors. And if you recognize that it is a 1 exponential I x is nothing but equal to minus I x is 1 minus I x plus I x whole square by 2 factorial and so on so forth. Okay. So, all these terms. So, this is nothing but for large time intervals, this is only the it is like an exponential minus I h t by h cross. Okay. So, u t 0. So, this is just the expansion of that. Okay. So, there are more terms that are going to be there like this I square h cross square by h square by h cross square and dt square and so on so forth. And so, this is equal to exponential minus I h t minus t 0 by h cross, and this is what we have been saying, that we will find out the form for that unitary operator, that which when applies or rather operates on the wave function would give me the time evolution of the operator and so on so forth. Okay. So, this is that in the simple form, this is the equation, and we can actually do it in another way, which is simpler way, or rather it is more intuitive. We do not have to go through this operator formalism. We can simply, so there is a second method of showing what is the form of this operator. So, if this is the formalism number 1, and we will just talk about a simpler formalism. Let us just your psi of r t, r and t, at least as far as non-relativistic mechanics goes, r and t are independent of each other. So, that tells you that g of r is equal to f of t, that is there is a clear function of r, and then there is another clear function of t. So, let us call them as g of r and f of t. So, if I put it in the Schrodinger equation, so it is like I psi del t r t, we are taking a time derivative. So, this g of r will not be affected. So, it is a g of r f dot of t. So, we have this that is equal to so this is equal to I h cross f dot of t, and that is equal to h of psi, which is equal to h and g of r f of t. So, now this is just like a normal algebraic equation. If you treat it like this, so you have a I h cross f dot by f, this f dot which is a function of t, f is a function of t as well, and this is like h which so this for a system in which the Hamiltonian does not explicitly depend on time. So, this h will give rise to a constant, and because you have two things which are so this is really that h g r by so this is g r h g r by g r. Okay, let us write it this way. Now, the left hand side is entirely a function of time, and this right hand side, if h does not include time explicitly, then it is a function of r. So, if they are equal to each other, then they have to be individually equal to be a constant, and this constant we call it as E. And so, f dot of t divided by f of t is equal to minus I e by h cross, because 1 over I is equal to minus I. Okay. So, that tells you that f of t is nothing but a constant into e to the power minus I e t by h cross, and if you are really looking for an operator, then this E is just the eigenvalue of some operator which we know as H. So, this again the operator that comes out, which is u of t, which is nothing but exponential minus I h t by h cos. Okay. So, this is how the wave function evolves with time. So, if you are given a wave function at an earlier time, you can multiply it by an exponential minus I h t, where h is a Hamiltonian of the system, and get the wave function at a later time. It is like saying the solving this Newton's law of motion. If you know x at a time t equal to 0 and v at a time t equal to 0, then you can generate the entire x at a later time, and so on and so forth. Okay. So, this is similar to that knowing the wave function at a certain time, one can actually build the wave function at a later time by using this operator, which is the time evolution operator, so to say, and which has a form which is given here. We will stop here for now, and then we will carry on with some solutions of Schrodinger equation in some simple problems, and in one dimension to begin with, and then we have to go to 3 dimensions in order to do the hydrogen atom problem, which is like a sphere. So, we have to solve Schrodinger equation in presence of a spherical symmetry, which is what we will do later. Thank you.